is equal to 0, means if the conductor is L vector is parallel to B vector, if the conductor is placed parallel to the magnetic field, no magnetic force acts on the conductor, and for theta is equal to 90 degree, sin 90 degree is equal to 1, and Fm is equal to ILB. The maximum magnetic force will act on the conductor when it is kept perpendicular to the direction of magnetic field. So, this is the force for a current carrying conductor placed inside the magnetic field. Now, the next is force between two parallel current carrying conductors Now we have two conductors which are parallel to each other and both are having the current I. This is conductor P and this is conductor Q. If we talk about the magnetic field for the both conductors, it will be in the circular lines around the conductor, and the direction can be given by right hand thumb rule. So, these circular lines show the direction of magnetic field around these conductors, straight conductors. Now, we are supposing that the current is flowing along the same direction in both the conductors. Let we have two conductors P and Q carrying currents I1 and I2 in the same directions. First of all, we have to find the force at the center point. Now, we will find the magnetic field due to this first conductor P at the center. So, when we apply right hand thumb rule, the direction of the magnetic field will be perpendicular. B1 is magnetic field due to current carrying conductor I1. This will be perpendicular at this point. So, if we take second conductor, the magnetic field due to the second conductor is B1, and at this point it will be perpendicular and outward. So, one magnetic field is acting inside the perpendicular to the board and other is perpendicular and outward to the board. Now, the magnetic field B1 is due to current carrying conductor P. This will be equal to mu naught I upon 2 pi A. The A is the distance between perpendicular distance between the two conductors. We have to find the magnetic field B1 at this second conductor. So, the distance is of current and the point where we have to find the magnetic field is A. Now, we have to find the force on conductor Q due to magnetic field B1. The force on the conductor Q is F2. This will be like this. F force is equal to current carrying conductor I1, length is L vector, and magnetic field due to current carrying conductor I2 and magnetic field is due to the first conductor. So L and B1 are perpendicular. We have F2 is equal to I2 L and B2 B1. Putting the value of V1, we have I2L mu naught I1 upon 2 pi A. This is equal to mu naught I1 I2 into L upon 2 pi A. So this is the first force acting on the second conductor F2. Now similarly we can find the force acting on the first conductor. This will be along this direction and it can be also given. Now the magnetic field B2 is equal to mu naught I2 2 pi A. Force F1 on conductor P due to magnetic field B2 is, the force is F1 vector, this is equal to I1 L vector cross B2 vector. L and B again are perpendicular, so F1 is equal to I1 L into B2. Putting the value of B2, we have I1 L mu naught I2 upon 2 pi A. Again this will be equal to mu naught I1 I2 L upon 2 pi A. So we see that force on the both the conductors will be same. F1 is equal to F2. If the current are flowing parallel in the same direction, then the forces will act opposite to each other. F1 vector will be equal to minus F2, means the two conductors will attract each other, and if the currents are opposite to each other, in that case the forces will be opposite and the conductors will repel each other. So we have to remember that the force due to current carrying conductor, two current carrying conductors is equal to mu naught I1 I2 into L upon 2 pi A. This can be also written as 2 mu naught I1 I2. Force per unit length, if we talk about 4 pi A, this is equal to mu naught upon 4 pi 2 I1 I2 upon A. If I1 is equal to I2 is equal to 1 ampere and the distance A is equal to 1 meter, we know that value of mu naught upon 4 pi is equal to 10 raised to power minus 7. So if we put these values, we have force per unit length is equal to 2 into 10 raised to power minus 7 Newton per meter. So this is all about the force for two current carrying conductors. Now we talk about force on a rectangular coil placed in a magnetic field. Suppose we have a rectangular coil and the current I is flowing. This is the direction of current I, and it is kept inside a magnetic field. This is the direction of magnetic field. The magnetic field can be generated by putting two magnetic poles, north and south pole, and keeping this rectangular coil inside the magnetic field. The magnetic field's direction is from north pole to south pole. Let us take the distance between this is coil ABCD. The length between A and D is x and length AB is equal to L. So the area of coil A is area of coil. This will be equal to L into x. Now the direction of current is in the upward direction and B is from left to right. Now the magnetic force F will be equal to, as we know, this is equal to, due to a straight conductor we know that magnetic field is equal to I L vector cross B vector. Since L and B are perpendicular, so we have F is equal to I L B. For the, this is the force acting on the AB edge. If we talk about force acting on the BC side, in this case the direction of current and magnetic field is same, so this will be 0, and same is for the side AD. Similarly, we can say the force acting on the side CD, this will be also equal to ILD B. But since the direction of current is, one is in the upward direction and other one is in the downward direction, so the one force will act in the inward direction, the magnetic force on the side AB, this will be in the inward direction, and perpendicular, and the force on side CD, this will be outward and perpendicular. Now two equal and opposite forces are acting on the two sides, so a couple or torque will act. Torque or couple will act on the coil, which will be equal to either force into perpendicular distance between the two sides. So the either force is F AB, that is we are talking about side AB, and the perpendicular distance is B. FAB is equal to IL B into B. This will be equal to IB L into B. Now we know that L into B, length into breadth, is equal to area of the coil. So we have torque is equal to IBA. So the force acting on the two different sides of the coil will rotate the coil, and it will produce a torque or couple. It will be equal to current, the value of current, into the value of magnetic field and area of the coil. This is for one coil. If we have n number of turns, in that case we multiply it by n, so we have NIBA. So this is the torque acting on the rectangular coil moving placed inside the magnetic field. Now the next is, that's all about my lecture. Thanks.